The topic for today, moving on, is going to be polynomial functions. And this corresponds with Chapter 4 in your textbook, Chapter 4. So we're moving on from Chapter 2 to Chapter 4 now. And so what is a polynomial function? We're actually familiar with polynomial functions, but a polynomial function, let's just throw down the definition right away, is any function of the form f of x equals an x to the n plus a n minus 1, x to the n minus 1, plus we're going to do dot 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 a to the 1x plus a naught. So essentially, this is a really fancy way of saying that the function itself is just a polynomial. The whole like a to the n, or x to the n minus 1 part just means that the polynomial can be any degree, right? And the degree of a polynomial function is just the highest power of x, right? The highest power of x that occurs in the function. Right? So if we're looking at this polynomial function right here, n, whatever n is, we're assuming that's the biggest number, is the highest power of x, and so the degree would be n for this one right here. But like I said, this is a very formal definition, right? It's a very formal definition, and really all it is telling you is that the polynomial, the function itself is just a polynomial. All right, so how do we identify a polynomial function? Well, a really basic example of one. Really basic example of a polynomial function would just be like y equals 3x to the fourth minus 2x cubed plus x squared plus x minus 1, right? There's a polynomial function, right? So by the definition we have also, by the way, quadratic functions are polynomial functions, right? They are definitely polynomial functions. What about the next one? F of x equals 7 minus 5x to the 8th. Is that a polynomial function based on our definition? Polynomial, polynomial. Is this one up? This is third one a polynomial? Yeah, I mean that expression is a polynomial, right? 7 minus 5x to the 8th. It's an incomplete polynomial because it doesn't have all of the intermediate powers. Like there's no x to the 7th, there's no x to the 6th, there's no x to the 5th. But that doesn't mean it's not a polynomial. It's just an incomplete polynomial. So if it doesn't have all of its terms, it's incomplete, but it still is a polynomial. So that's a polynomial. Is the function, what if it's just like 3x to the fourth, if it's a single term, if it's a monomial? Is a monomial a type of polynomial? It is, isn't it? Just a one-term polynomial. And we're going to start calling these in a second power functions. Now, on the other hand, so these are all examples of polynomial functions, right? Things that sort of look a little bit like polynomial functions that aren't polynomial functions on the other hand, look like this. Things that make a function not a polynomial function. All right, those would be a root, any type of root, which also means any type of fractional exponent. Oh, I should be really specific because it's a root of x, a fractional exponent on x. Roots, fractional exponents, negative exponents on x, which means if x is in the denominator, right? Log or exponential. Exponential means if it's like a to the x, that's not a polynomial function. Any type of trigonometric function is not a polynomial function. And that's trig functions. Piecewise functions, of course, are not. Which means the floor function. It's not a polynomial function. All of those things are not polynomial functions. So examples of that would be like the function f of x equals x to the 2/3 plus square root of x. Like that's not a polynomial function because we have fractional exponents, we have roots, not polynomial, because those aren't polynomials. Another example of a function that's not a polynomial function is like 1 over x. The reciprocal function, maybe it's plus 3. The reciprocal function is not a polynomial function. On the other hand, we know that polynomial functions do come sort of packaged in other forms. F of x equals 2x squared times x minus 1 squared. Now, is that a polynomial function based on what we know about simplifying expressions like that?
Yeah.
It is, right? Because I can write it in a polynomial form if I just simplify it. X minus 1 squared is x squared minus 2x plus 1. And then I can distribute the 2x squared, and I get 2x to the 4th minus 4x cubed plus 2x squared. Right, so that looks like a polynomial function now if I go ahead and simplify it. So this is what we call the factored form of this particular polynomial function. And this is the simplified form of that same function. What's the degree?
4.
Yep, so the degree of this function is 4. So certain things about polynomial functions. Let me just, so degrees and classifications here. So, degree 0 function would just be f of x equals 0, right? A degree 1 function would just be f of x equals some constant value, right, which we'll just call a naught for now. So that's a constant function. This is the 0. This is called the 0 function. This is a constant function just because it's the same value all the time. Degree 2 function Oh, I'm sorry. I screwed this up. So there's actually something lower than degree 0, and that is the function I'm talking about here. So I got to change my degrees. I always get these off by 1. So the function f of x equals 0 is actually just considered a no degree function, doesn't have a degree. This is going to be a degree 1 function. Sorry, degree 0 function is a constant function. So it actually has a degree, it's just a 0. A degree 1 function is a function like the following. What type of function would we call that? Just a to the 1 times x plus some, and a to the 1 and a naught are both constants, by the way. What type of function do we call that one?
Linear.
That's a linear function, yep. So a linear function is actually a type of, it's a type of polynomial function, actually, it turns out. All right, moving on. If we have like a degree 2 function, that function looks like this. A2x squared plus a1x plus a naught. That one you're familiar with. That's just a what type of function? Quadratic function. This is just a degree 2 polynomial. And a degree 3, we'll stop at degree 3, would be, of course, f of x equals a sub 3 x cubed plus a sub 2 x squared plus a sub 1 x plus a naught. That's just going to be a cubic. I'm going to call that a cubic function from now on. And then we do have names for some of the higher degrees as well, like quartic functions and so forth. But we're not so concerned with those types of functions. So, a sort of subtype of polynomial functions is called a power function. Right, and a power function is just a single term polynomial function. Sometimes called a single term polynomial is a monomial, right? So they're of the form f of x equals ax to the n. They'll all sort of look like that. Where, of course, a can't be 0, that it wouldn't make sense, and n is greater than 0, right? So n is like 1, 2, 3, 4, and n is an integer. Because once again, if n is like a fractional quantity, then it's not a polynomial function anymore at that point. So n has to be an integer value, like 1, 2, 3, 4, 5, and it also has to be greater than 0. So it has to be a whole number, or a counting number, essentially. 1, 2, 3, 4, 5, 6. And so let's go ahead, actually, and let's just plug some of these functions into the graphing calculator and sort of explore graphically what the value of n does, what the value of a, what effect that has on it, and then ultimately, how can we use transformations to graph different power functions. Come to that later. All right, so let's go ahead and here. All right, let's go ahead and just graph some basic power functions here. So like a really basic one. A really basic power function would just, of course, be y equals x squared, which we know is just your basic parabola. What happens if we have x cubed? We talked about the cubic function, sort of looks like that, right? What if we go up to x to the 4th? Well, sort of looks like a parabola a little bit, doesn't it? It's sort of a parabola that's flatter at the bottom and steeper on the sides. Right, so my observation would be that when x is less than 1, it sort of flattens out more quickly. But when x is greater than 1, it blows up a lot more quickly, right? In this, in the upper region right here, it gets larger more quickly. But down around 0, 0 there, it sort of flattens out more. Let's look at, I'm going to just go up and, okay, I'll do x to the 5th here. And x to the 5th, same observation compared to x cubed. X to the 5th sort of looks a lot like x cubed, except it's flatter around the origin, and it's steeper once you get past 1 and negative 1. Right? X to the 6th also looks sort of like a parabola, flatter yet near the origin, steeper yet outside of 1 and negative 1. And you're going to see sort of that same pattern continue to repeat itself, where even values of x all look like parabolas that get successively flatter on the bottom and steeper on the sides, and the odd powers do the same thing. They get flatter near the origin and steeper farther away from the origin, right? And so they're all going to have that basic look to them, these power functions that we're dealing with right here. And so let's go ahead and come up with some basic ideas. First of all, for odd powers, like x to the 9th or x to the 7th or x to the 5th, do they have any type of symmetry? Is there symmetry there?
For the odd powers?
Yeah, for the odd powers. Looking at this one, right, this is being an example of an odd power.
Symmetry about the origin?
Yeah, they have symmetry about the origin, which means they are what type of function? Odd functions, right? Whereas like x to the 10th here has what type of symmetry? Symmetry about the y-axis. So it is in. So when the power is odd, it's an odd function. When the power is even, it's an even function. That's pretty easy to remember, right? And what about domain and range? What's the domain of this even function and theoretically all the even power functions? What's the domain? Values of x. That x can be here. Yep, all real numbers. And what would the range be? Where does y go to and from?
0 to infinity.
Yep, 0 to infinity. And that's going to be true for all even functions, or all even power functions, right? X to the 10th, x to the 12th, they're going to have a domain of all real numbers and a range from 0 to infinity. Odd functions, on the other hand, are going to have a domain and range that are both all real numbers, right? Y goes from negative infinity to infinity, and x also goes from negative infinity to infinity. And we talked about the fact that with the odd functions, higher powers of the odd function is going to flatten out the area near the origin more and make the areas to the outside of x equals 1 and x equals negative 1 even steeper, right? So it gets flatter in some parts, steeper in other parts as the power gets larger. And the same is true for the even powers as well. So let's go ahead and summarize that. So for even power functions, they are even functions, meaning they are symmetric about the origin. And this is where that whole name came from. They're even functions, and that means they're symmetric about y-axis. The domain is always negative infinity to infinity, and the range is always, it's inclusive of 0, right? To infinity. And if n is bigger, as n gets bigger, it's flatter near the origin, steeper and it's steeper, I should say where the absolute value of x is greater than 1. So to the outside of 1 and negative 1, right? That's when it gets steeper. But between negative 1 and 1, it's flatter. And now for odd power functions. They are all odd functions, symmetric about the origin, their domain and the range are both negative infinity to infinity, and the same thing is true that if, as n is larger, it is flatter near the origin and steeper where x, absolute value of x is greater than 1 on the graph. All right, and so we can use these ideas to graph transformations of power functions. So I'll give you a couple examples. Why don't you go ahead and graph for me f of x equals x minus 1 to the 5th plus 2, and also graph for me negative x to the 8th plus or minus 3. So go ahead and, using what you know about transformations of functions, graph both of those power functions for me. Or those, because those are transformations of power functions, right? It's worth noting really quickly before we get going here, these are transformations of power functions, right? But are these actually power functions after we've transformed them, or do they become not power functions afterwards? Is this a power function actually? Does it only have one term? No, so that's actually, if you transform the power function, it's no longer a power function, but we can still graph it knowing what we know about the original power function. Same thing here. With this one right here, x minus 1 to the 5th plus 2, if I simplify that out, it's got multiple terms, therefore it's no longer a power function, but it is a transformation of the power function x to the 5th, and so we can graph it knowing about what x to the 5th looks like. So go ahead and use transformations to graph both of those. Okay, let's go ahead here and graph these both. We know that x to the 5th roughly looks like the cubic function, but maybe a little bit flatter. It doesn't have to be perfect as long as we're somewhere in the right ballpark. That's all that really matters for this type of a question. So looking at this function, we know the parent function is x to the 5th. We're going to shift it, if it's x minus 1 on the inside and plus 2 on the outside, it'll be shifted to the right by 1 and up 2. So right 1 and up 1, 2. Right, and so it's going to look like the following. Right, something like that. And the other one is x to the 8th is the parent function, so it's going to look like a parabola with really steep sides and a really flat base, essentially. The transformations we have, though, is we have a negative on the outside here, so we're going to do a rotation or a reflection around the x-axis, right? So we're going to flip it over the x-axis, and we're going to push it down by 3. So it's got to go down by 3, 1, 2, 3, and it's flipped over the x-axis, so it's going to look roughly like that, right? Really flat at the base, not totally flat at the base like it might seem like based on how I drew it, but fairly flat at the base, and then going straight down there. Okay? All right, let's talk a little bit about smoothness and continuity. polynomial functions. That's one of their greatest properties, that they are continuous. First of all, for a function to be continuous, there can be no breaks in the function. To be a smooth function, there's no corners or cusps. Right, so it's continuous, smooth. Smooth is sort of a very informal word. Eventually, when you get to calculus, we'll call that differentiable. But for now, we're going to call it smooth. And so an example of a continuous function would be something like this. So this following function would be both continuous and smooth, right? The next function here is continuous but not smooth, right? Because it has those. There's no breaks, right? Whoops. So it is continuous, but it's not a smooth function in the sense of what we're talking about. And this last one here is an example of a function that's neither continuous or smooth, right? There's breaks along the way, and there's a corner up here, or cusp, whatever you want to call it. So this is neither continuous or smooth. So that's what we need about. That's what I mean by continuity. Whether a function is continuous or not, whether a function is smooth. 3 examples that sort of illustrate that point. Now, with polynomial functions, let's look at a couple examples here. Look at a basic power function. We know what that looks like, so that's easy, like x to the 5th. Let's look at another one like x to the f of x equals x cubed minus 3x squared, minus 3x squared minus x plus 1. And then maybe we'll also look at one more, f of x equals x to the 5th minus x plus minus 2, let's say. So this isn't every possible polynomial function, obviously, but these are some basic examples of polynomial functions. Let's go ahead and graph them on our TI-84 calculators now. Let's actually make this last one x to the 4th. X to the 4th minus x minus 2. So we'll use that one instead. All right, if we go ahead and graph all of those in our calculator, the graphs look like the following. The graph of x to the 5th, we're familiar with that one. It's a power function. This cubic function looks roughly like that, and then we have this x to the 4th function, which sort of a little asymmetrical, kind of goes farther down to the right than it does to the left. But in all 3 cases, these functions are all continuous. There's no breaks, and they're smooth. Right? And that's going to be true for all polynomial functions. And that's really important, as we'll see later on. So all polynomial functions are continuous and smooth. Okay, the last thing we want to do today is we're going to talk about zeros of a polynomial function. Right, and so for the time being, we're going to start looking at functions, or we're going to look at the next few polynomial functions we're going to take a look at will all be in their factored form. So they're factored form. So for example, the functions will look like this. or similar to this, where they'll be completely factored out. And since we're about to be identifying zeros, that's going to be important, right? So the zero of a polynomial function and the zero for any function are just, that's sort of a fancy way of saying the x-intercepts, right? The x-intercepts of the function. So if we're using our first example up here, we want to find the x-intercepts of that function. We'll take f of x, which is equal to 3 times x minus 2 times x plus 1 squared, and we'll set that equal to 0 and solve this equation right here, and that will give us the zeros of the function. And with polynomial functions, as we're going to see later, they can all be factored, for the most part, can be factored out like this. And if they're in their factored form and we set them equal to 0, we're going to use the zero product property, right? To go ahead and say that, well, if this equals 0, then either x minus 2 equals 0, right? Or x plus 1 equals 0. Therefore, my two zeros would have to be negative 1 or 2. Right? Those are going to be my two x-intercepts of my function. So even though I have maybe no other clue what this function looks like, I do know that it has x-intercepts at negative 1 and 2. So let's go to the next page here. One thing we're going to take a look at, right? Sorry, let's go ahead and summarize zeros first of all. So to summarize what we know about zeros of functions, so if, let's say, r is a zero of the function f of x, then the following facts are true about r. Then r is an x-intercept. X minus r, it must, and this is a really important fact, x minus r then has to be a factor of the function f of x, right? It should be able to be factored out where x minus r is a factor if r is going to be a 0, because that's how we found r in the first place, is by factoring it and setting those equal to 0 using the zero product property. And x minus r equals 0 means x equals r, right? And lastly, that also means it's the same thing as saying r is a solution of the equation f of x equals 0. Right? It's a solution to that equation, which means that x minus r is a factor of f of x, which means that r is an x-intercept. All those things essentially are saying the same exact thing right there. Okay? So let's go ahead and answer the following question. I ask you to find a polynomial function with zeros of, let's say, 2, negative 1, and 3 that has a degree of 3. Why don't you go ahead and, based on what you know about zeros now, go ahead and write a function that has those zeros. All right, so what do we think, Kevin? What would be a polynomial function f of x that's degree 3 that would have those 3 functions as zeros?
It would be
Luke, what do you think? If it has zeros of 2, negative 1, and 3,
X minus 2
that's got to be a factor, right?
times x plus 1
So yeah, x plus 1's a factor, yeah.
times x minus 3.
And if we multiply three binomials together that are each order 1, that's going to give us a polynomial of order 3, right? Our highest power will be x cubed. Does that make sense? Because x minus 2 is a factor, that means 2 is a 0. Because x plus 1 is a factor, negative 1 has to be a 0. And because x minus 3 is a factor, 3 has to be a 0. Now what if I asked you the same question, but I said with degree 4? What could you do to find a polynomial that has degree 4, right, that has those same 3 intercepts? And my hint is there's more than one solution to that, one way to answer that question. How can I make it degree 4 but still have the same exact intercepts? What if I did x minus 2 times x plus 1 times x minus 3 squared? That's going to bring it up to degree 4, right? Because you square that binomial, you have a quadratic times 2 more binomials of order 1, then you're going to get an x to the 4th as your highest power. And it's still going to have the same exact intercepts. All right, so what's going to be curious is to see, okay, these have these same exact x-intercepts, but how are they going to look different if they're different degrees? Because this one has an x minus 3 squared versus just an x minus 3, and this is a difference of what we're going to call multiplicity. I'm going to try and write that somewhere else. What is the multiplicity of a 0? So multiplicity just means that what is the power of this factor, right? This has multiplicity 1, right? That's a multiplicity of 1, and this one's a multiplicity of 2. How is that going to change how the graph looks? So let's go ahead and graph on the next page here. We'll graph both of these on our graphing calculator and see how they look different. F of x equals x minus 3 times x plus 1 times x minus 2, and the function f of x equals x minus 3 times x plus 1 times x minus 2 squared. So we'll go ahead and graph those. So if we go ahead and graph both of these, we see that they have the same x-intercepts, but in the case of this first one here, it crosses the x-axis at 2, and it just touches the x-axis at 2 in the second one here when the multiplicity is 2. So the multiplicity of the root x minus 2 is 1 up here, right? This has a multiplicity of 1. And this has a multiplicity of 2. Sorry, let me go fix this. And we see that the difference is, in the case of negative 1 and 3, they both, because these both have multiplicity 1, they both fully cross the x-axis at 1 and 3, right? Whereas with 2, it crosses when the multiplicity is 1, and it just touches it when the multiplicity is 2. Interesting. Let's go ahead and investigate a couple of more examples to see if we can maybe pin down this behavior. So let's look at the functions. What if we have one? I'm just going to make an even simpler function. What if we have the function x minus 2 to the third and the function x minus 2 to the fourth, and I'll even do the function f, let's even do f of x equals x minus 2 to the fifth. Graph all three of those and look at, so these are all going to have a single 0. These are all polynomial functions that have a single 0 at 2, but they're all going to have slightly different behavior. First of all, the multiplicity of this root here is 3. The multiplicity of this root is 4. And the multiplicity of this root is 5. So let's see how that multiplicity changes the graph of these three functions. So what's the trend that we are seeing here? When the multiplicity is even, it seems to always just touch the x-axis but not actually cross it. But when the multiplicity is odd, it seems like it usually crosses the x-axis. We've seen that in the past two examples. And so that's the rule we're going to end up with here. With the multiplicity of zeros of a polynomial function. Whoops, let's spell that correctly first of all. So the multiplicity of zeros of a polynomial function, right, is that if the multiplicity is even, it touches the x-axis at 0 without crossing it. At x equals r if r is the 0, right? On the other hand, if the multiplicity is odd, it crosses. It actually goes from above to below or from below to above the x-axis at x equals r. And so right away, if you have the fully factored version of the polynomial function, you know the zeros, and you can identify at each zero, does the function actually cross the x-axis, or does it just touch the x-axis and then go back down or back up, depending on where it started, right? And that will, and combined with some more strategies that we're going to use in the next lesson, is going to allow us to start piecing together what the graph of these higher order polynomial functions look like, assuming we can factor them, okay? So we'll get into that more in the next lesson. That'll conclude the lesson for today. Your assignment will be on the next page here. So this is the assignment for tonight. Since we finished Chapter 2 over the weekend, I'll come up with a Chapter 2 unit test for you guys. It'll just be a practice test that you can take it home. I'll give you the solution set, and so you can figure out how you're doing on Chapter 2. In the meantime, we're just going to keep pushing forward on Chapter 4, polynomial and rational functions. And the next class will not be until Monday, this coming Monday, and that is July the 7th, I believe, July the 7th. Have a great 4th of July, everybody.